Good day. Today we will discuss about calculating the upper cutoff frequency using zero value time constant method. Otherwise the method is called as open circuit time constant method. The upper cutoff frequency can be calculated by using zero value time constant method. The procedure is as follows. Step number 1 is we have to draw the high frequency equivalent circuit diagram. Step number 2 is the circuit may have the more than one capacitor, so we have to consider one capacitor at a time and we have to open all other capacitors. Step number 3 is remove the sources which are connected with capacitor terminals and null the sources those are not connected to the capacitor terminals. Step number 4 is open the capacitor from the circuit. Step number 5 is excite the capacitor using test voltage or test current. Step number 6 is compute effective resistance R effective seen by the capacitor. Step number 7 is calculate the time constant tau. Tau is the product of R effective into C. Now we have step number 8 is now we have to repeat this procedure for rest of the capacitance. After doing the tau value, after calculating the tau for all the capacitors, we can compute the overall upper cutoff frequency. The upper cutoff frequency can be calculated by using this formula. F3 dB is 1 over 2 pi summation of I equal to 1 to n into tau I. So this is a circuit is given for this is a simple common emitter amplifier circuit. For this simple common emitter amplifier circuit, we are going to draw the we are going to find the upper cutoff frequency. As per step number 1, we have to draw the high frequency equivalent circuit diagram. So now we will draw the high frequency equivalent circuit diagram. High frequency equivalent circuit diagram is a combination of high frequency model of a device and its biasing element. GMV pi R naught C mu C pi R pi. So this is a high frequency equivalent model of a device, BJT device. This BJT device high frequency model is this one. Now we have to draw the biasing element. While drawing the high frequency equivalent circuit diagram, the coupling bypass capacitor will be shorted. Coupling and bypass capacitor will be treated as short circuited one. So let us assume virtually we are standing here and DC source will be shorted. Okay, DC voltage source will be shorted. Now let us see when we stand this point R1 parallel to R2, R1 parallel to R2, let us say R1 parallel to R2, then we have the RS resistance, Vs is connected via Rs, Vs. Let us go and stand at the emitter node. What we can see, emitter node we can see it is directly connected to ground. Base, collector, emitter. Let us go and stand at the collector node. What we can see, RC parallel to RL. RC parallel to RL. Now then here we are going to measure the output voltage V0. Connect all the ground terminals together. Okay, let us group the resistances to simplify the circuit. R1 parallel to R2 parallel to R pi as RB, R1 parallel to R2 parallel to R pi. Similarly, R0 parallel to RC parallel to RL as RL effective. RL effective is R0 parallel to RC parallel to RL. Now I will draw the reduced circuit diagram. Vs, Rs, RB, capacitor C pi, C mu, GMV pi, RL effective. and V naught. Okay, so now we have finished the step number 1. Step number 1 is draw high frequency equivalent circuit diagram using the procedure of high frequency analysis. Already we know that the procedure of high frequency analysis. By using the procedure of high frequency analysis, we have drawn the high frequency equivalent circuit diagram. Now, as per step number 2, consider one capacitor at a time, open all other capacitors. So let us consider C pi and open C mu. There are two capacitors, C pi and C mu. Let us consider C pi now, then open C mu. Vs, Rs, Rb. We are going to consider C pi. C pi and open C mu. Let us open the C mu. This one is GMV pi, RL effective. And V naught. So next step, we completed step number 1 and step number 2. Step number 3 is remove the sources which are connected to the capacitor terminals and all the sources those are not connected to the capacitor terminal. This is a capacitor, let us say A and B. Okay, there is no source connected across this capacitor terminal. Okay, so both V naught is the output source, Vs is the input source. These two sources are not connected with the capacitor terminal. So we can null. How to null it? We know that nulling the voltage source will be the shorting the voltage source. Let us ground the voltage sources. Rs, then we have Rb, capacitor C pi. Here it is open circuited, GMV pi, RL effective. Again output voltage source is grounded. Here also on ground. So once again reduce the circuit diagram. With respect to this node Rs parallel to Rb, I can say, let me say R effective. Let me put R effective and capacitor C pi. That's all. This side GMV pi and short parallel with a passive element will be treated as a short. Okay. The next step is step number 4. Open the capacitor from the circuit. Then step number 5 is excite the capacitor using test voltage or test current. So let us open the capacitor from the circuit. This is a C pi is the capacitor which we are going to consider. Now I open the capacitor. Assume now the capacitor is charged by some voltage. So value is V test. Here the resistance value is R effective. Determine the next step is compute the effective resistance seen by the capacitor. Let me say effective resistance is R effective 1 for tau 1. So what is the effective resistance seen by the capacitor? Effective resistance seen by the capacitor is R effective, which is nothing but Rs parallel to Rb. Okay. So what is the tau 1? Tau 1 is R effective 1 into C pi. So again we will repeat it. Calculate time constant tau. Now first capacitor C pi we are considering. So tau 1 is R effective 1 into C pi. The next step is repeat the procedure for all other capacitors. Now we are consider C pi. So we will consider C mu. There are only two capacitors. Now we have to repeat the procedure for C mu. The same procedure. Step number 1 is draw high frequency equivalent circuit diagram. Already we have drawn. Step number 2 is we have to consider the next capacitor. Next capacitor is C mu. Let us consider the C mu alone. So once again I will draw the reduced circuit diagram. Vs by considering the C mu. Vs, Rs. This we know that already we grouped as RB, RB. Then as per the procedure we have to remove the C pi because we are going to consider the C mu. C pi is open. You have the C mu, GM R naught, GM V pi. Then we have R naught parallel to RC parallel to RL, that is RL effective. Here V naught, output voltage source V naught. Okay, so next step is, what is next step? So remove the sources which are connected with the capacitor terminal and null the sources those are not connected to the capacitor terminal. So this capacitor C mu is connected to V naught. So we have to remove this source. But Vs is not connected with the capacitor terminal. Let me say A and B are the capacitor terminals. V naught is connected, so we have to remove. Remove means just removing the voltage source. Null means we have to kill. This source is not connected to the capacitor terminal, so we have to kill it, null it. How to nullify the voltage source? By the way of shorting the voltage source. So again I'll draw it. Rs, RB, capacitor C mu, GMV pi, RL effective. Okay. I will draw the by considering the capacitor C mu, I will draw the circuit diagram. R effective, this is R effective. Now C mu will have the potential of V test. So here we have GMV pi and RL effective. Okay. So the loop current supplied by the, once again draw the circuit. R effective. The capacitor will supply the current of I test. Let us assume the capacitor, charged capacitor, V test charged capacitor will supply the current of I test. GMV pi, RL effective. Okay, when I test current flows, it makes a drop. Let us name it as V pi. The GMV pi is the depend this point potential. So it makes the drop of V naught, but we assume the drop across the RL effective is V naught. This is the actual current flow. So we can say what is V naught? V naught is the drop across RL effective. So when you apply the KCL at this junction A, there are two currents leaving the junction. One is I test, another one is GMV pi. So you can say I test plus GMV pi into RL effective. Okay, what is V test? V test is the difference of these two potential. One is V pi, another one is V naught. So what is R effective 2? Effective resistance seen by this capacitor R effective 2 is V test by I test. V test is V pi that means input side node B voltage minus V naught potential across the node A divided by I test. V pi is, we can retain V pi as it is as of now. V pi, what is V naught? V naught we can write V naught equal to minus Gm V pi, the current leaves the junction. So, and also this one, here also we can put minus sign. Gm V pi I test into plus I test into RL effective. Okay, already we have written. So, minus of minus become plus because actual current flows opposite to the reference direction. That's why we are getting this minus sign. V pi minus of minus Gm V pi plus I test into RL effective. Okay, divided by I test. So, V pi minus of minus become plus Gm V pi, okay, plus Gm V pi into RL effective plus I test into RL effective divided by I test. So, what is V pi? V pi is the drop across R effective. So, we can define V pi equal to I test into R effective. Okay, so now the equation become I test into R effective, again Gm V pi, Gm into V pi is I test into R effective, I test into R effective into RL effective plus I test into RL effective, everything divided by I test. Now in numerator term I test is a common, I test, I test, I test. We can take that I test outside. So this is the formula for R effective 2. R effective 2 is I test into R effective plus, so next one is we can say RL effective plus Gm into R effective into RL effective divided by I test. So I test can cancel. R effective 2 is R effective plus RL effective plus Gm R effective into RL effective. So simply we can, in a single stroke we can calculate this one. Whenever we are getting like this circuit, what is the effective resistance? Effective resistance is the input resistance plus output resistance plus Gm into input resistance into output resistance. Let's see, R effective is the input resistance, RL effective is the output resistance, Gm transconductance gain into R effective into RL effective. So what is the tau 2? Tau 2 is a product of R effective 2 into C mu. Okay. Now, so what is the next one? We have completed the 6 steps. Yeah, sorry, 8 steps, and we found that. So next step will be the so we have to repeat the procedure for other capacitor. But this circuit has only 2 capacitor. We finish the procedure. Now the last one is calculate the upper 3 dB cutoff frequency. How to calculate upper 3 dB cutoff frequency? Upper 3 dB cutoff frequency is a 1 over 2 pi into summation of tau I equal to 1 to n. Here n equal to 2. So 1 over 2 pi tau 1 plus tau 2. So 1 over 2 pi tau 1 is R effective into C pi plus tau 2 is R effective plus RL effective plus Gm R effective into RL effective into C mu. Okay, by using this formula we can calculate the upper cutoff frequency of a common emitter amplifier. So thank you, we'll meet next class.